Hello and welcome back to the machine learning video series. In the last video, we talked about the gradient descent. I'm sure most of you still have no idea how that actually works, and it is a genuine issue. It involves calculus after all. Also, you do not need to go that deep into the concepts. You only need to know how it works and provides output. It's driving a car. You do not know how the actual mechanics of the car works, but you know how it works in the outside world to decide which model would suit you better. So, to give a test drive of gradient descent, let's look at an example here. Let us try to visualize the process. For this example, we will take a very simple data frame of only one feature, x. We can look at the data frame and tell that x is always same as y. The equation of a perfect line would be x equal to y or x minus y equal to 0. But we want our machine to understand this. As we had discussed, we can assume a random value of w and b, and just to avoid calculations and make it easy to understand, let's take w and b equal to 0. Now, j was our cost function and h of x function is the representation of y equal to wx plus b. Hence, with the value of w and b, our hypothesis would be y equal to 0, that is, predictions will always be 0, irrespective of x. Of course, this is nowhere close to the actual correct hypothesis. If we try to calculate the cost function with our assumed values, we will have to find the squared difference of each point in dataset with our prediction. Since prediction is 0, the cost function is nothing but sum of squares of all y values. Note that when we talk about cost function, we mean the sum cost about all the points in the dataset. Hence, our cost with w and b both equal to 0 is 3.75. The next step is to update the value of w and b such that the total cost comes down. We know that we have to differentiate the cost function to find updated values. The equation for differentiating is shown here. Take a minute to check how we got here. We have j, that is our cost function in terms of w and in terms of b. For the sake of illustration and ease of calculation, let our learning rate alpha be equal to 1. There are 4 points in our data frame, so m becomes 4. We know that for updating, we have to multiply the calculated value by learning rate and then subtract it from its older value. This here is current value, which we have assumed, and this here is the actual value, which we will calculate. But both the old values of w and b are 0 because we had assumed it for easier calculations. And the first point in our data is x equal to 1 and y equal to 1. So, for x equal to 1, our model predicts 0 into 1 plus 0, that is 0. The actual value is 1. Hence, the updated w becomes 1 by 4 or 0.25. Similarly, the updated b also becomes 0.25. Now, using these, if we calculate the new cost function, we see that it comes out to be 1.671. That is, we have put the new values of w and b in this formula here. Now, the previous cost function was 3.75. That is, the error loss is decreasing. A very important thing to observe and note is that the values of w and b are both updated together. They must always be updated together. In one iteration, many people update w properly and then make the mistake of using the newly updated w to update the value of b. This is wrong. The values of w and b must be updated using one pair of old values only. If not done correctly, the equations will change and our cost function might never converge to the minima. We have only used one single point to improve our model till now, taking the next point in our data set where x equal to 2 and y equal to 2. Now this time our old w and b become what we have calculated in the last slide, that is 0.25. So w equal to 0.25, b equal to 0.25, x equal to 2 and y equal to 2. Put all of them in the formula, we get w equal to 0.875 and similarly b equal to 0.56. Note that in order to update equation for b, we have used w equal to 0.25, which was the old value, and not W equal to 0.875, which was calculated in this step itself. Now using these new values of W and B, if we try to calculate cost function again, we would write the new equation with all values of x, taking W equal to 0.875 and B equal to 0.56. The cost turns out to be 0.408. In the previous step, our cost was 1.617. So this is significant improvement. The cost is less than 1. Now we understand how gradient descent works. The process is repeated for each point in the data frame. This time, for the point where x equal to 3 and y equal to 3, we repeat the process. W is updated with the value that was calculated in the previous iteration, that is 0.875, and B is 0.56. The learning rate is still 1. In some advanced problems, we might need to change the learning rate also as we proceed with the training. Now, after following the same steps and calculating with the formula, the new value comes out to be W equal to 0.73 and B equal to 0.515. Ultimately, the new cost function is 0.0551. You can see in the table that the predicted values are now quite close to the actual values. Now we repeat for the last value in our data set. The final values of W and B are 1.28 and 0.51. The illustration is successful as we got values which are somewhat close to the actual values. We know that the actual values would have been 1 for W and 0 for B. With more number of points, we would have reached the actual values. Moreover, we have only used every point in our dataset once. In practice, we need to go through our dataset again and again. Of course, we would not run through our dataset so many times that it starts to overfit, but we certainly use every data point more than once. And don't worry, this is just a concept that you all need to understand. The actual calculations will be done by the computer. Now there is something to note here. The cost actually increased from the third data point to the fourth data point. The following plots make it more intuitive. We started off with W and B equal to 0. After that, the value started increasing. Notice that the third and fourth plots have comparable error, but the third plot is actually better. This is evident from the fact that even the cost has increased from the third to fourth data point. This might be a case of slight overfitting. This is not impossible since our learning rate was 1, which is a really large value in practice. Commonly used values of the learning rate are 0.1 or 0.3 or multiples of 0.3. We could not have had a really small learning rate because we had only 4 samples in the dataset. Gradient descent is the basic approach of machine learning, and its modifications are used even in deep learning concepts like advanced artificial neural networks. This is all for this video. Thank you.